so Rob went over the observation that we made at Arecibo on the Black Widow pulsar about these amazing lens pulses. So I'd like to talk about it a little bit about how we think this happens. And a lot of this is due to Ishan, who worked closely with, who could not be here today. So just to outline, I'm just going to go over the XSDM that we can measure just near the eclipse, and then go over a little bit into the theory about how we think the lensing occurs, talk about wave optics, and talk about the simulation that we make trying to fit that to data. Okay, so near the eclipse, we can, so here you have the measure x-axis is basically in seconds since the start of the file. So this is real time, and then in y-axis is the XSDM. So you have the eclipse right here, and then near it we can fold, for example, 2 seconds of pulses, and then compare that to a pulse outside the eclipse, the average pulse outside the eclipse, and then that gives you a delay, and then delay gives you extra DM. So if you zoom in into this region, where a lot of strong lensing occurs that you saw in RobSoc, so a lot of strong lensing occurs in this low DM region. And I just want to emphasize that the lensing is due to the small scale structure that you see, and not this large overall structure. Okay, so just going over how the normal framework of lensing, which is due. So you have your pulsar emits a EM wave. It scatters at some screen and then comes to us. And the actual EM wave that we measure is integrated over all the paths that the wave can take, weighted by the phase, and where the phase added up currently is what we can, what we measure as the electric field. So the phase is basically your geometric phase, which is how far away the wave, how much more path, how much more delay the wave took compared to line of sight, plus your DM screen. And then we can do this integral in general because DM is in general a unknown function. If DM was 0, then it's just a Gaussian integral, which is easy to do. And this minus sign here is because we call that in cold plasma, the phase velocity is faster than the speed of light. So in the presence of excess plasma, your phases are going to be advanced. So we put a minus sign there. So if you take a 1D lens just for simplicity, notice that this exponential of I to something is going to be oscillatory. And the biggest contribution is when phi doesn't change much. So you can simply approximate the integral by the stationary points of your phase that you expand to second order. So we call these stationary point images. There were some discussions about what images mean. So this is how I define an image. And this approximation to second order in phase is what's called the diagonal approximation. Or this framework is called geometrical optics. So each stationary point has its own magnification, which is proportional to the inverse second derivative of the phase. And that's easy to see because if your phase parabola is thinner, then you're adding up over a smaller region of phase. And if your parabola is wider, then you're currently adding up a large region. So when does...
Defining magnification here as in the electric field, not in the intensity.
This is in the intensity. In the electric field, you would be square root second derivative, I think.
Because it's still square.
Yeah. So when does this approximation work well? Essentially, it works well if you can fit a parabola to the stationary point, and it approximates the phase wall up to a difference of phi in phase, because up to a difference of phi in phase, you can add up UAs coherently. So this is a figure from Gwen et al. In 1998. So you have your geometric phase and your DM phase, and the sum of them is your total phase, and you see those points are your images. Because far away from the line of sight, the geometric phase dominate. You can only have images in a confined region, and that's what you call your scattering disk. So this approximation is not good in our case. So why? So if you just put in some numbers in your eclipse and then compare the phases, so you convert your delays into a phase, you convert and then you put in the geometric phase, and you see that basically the curvature in the geometric phase and the curvature in the dispersive phase is similar. So when you add them up, the second derivative of total phase will often vanish. So the echo-null limit will in general fail because it predicts infinite magnification. But that's okay because it just means that your approximation is not good, so you go to the next order. So the regions where second derivative is 0, we call that caustics. It's basically regions where you have a boundary from one image region transitioning to 3 image region, or 3 image region transitioning into 1 image region. So caustics are basically where images merge. So we like to put this into just doing the optical path integral. But to do that, we need a final resolution on the DM, because clearly this, if you just put this in, you cannot get a good enough curvature. So we can probe DN in a finer scale just by folding less pulses. So instead of folding 2 seconds of pulses, we're going to fold 100 milliseconds of pulses. And that's about a Fresnel scale of at the lens screen, if you assume that the screen moves with the companion. So you measure that, and then you can measure the DM variation, and you see that it follows a power law and then hits some noise floor. So you take the power law, and then you can simulate a screen, and you can impose some various cutoffs and use that as a parameter of your screen.
What is the scale on the left of the lower plot? I can't read.
Oh, it's. Oh. So 10 to the minus 12, 10, 8, and 6.
So it's a factor of 10 to the 4?
Yes.
It's important.
Okay. Yes, that's right.
And the minus 2 seems very, very close to minus 2. Is that a significant number? Does anyone know that? Or is that sort of, oh well?
Yeah, I'm not sure about that. That's what I've been wondering about as well. Yeah, so you take the power law, put in some higher scale cutoff, and then put that in your diffraction integral code, which is originally written by Ishan, and then I added the wave optics part. So for a fairly low cutoff, oh, this is terrible resolution. You simulate about 1 minute of data over some large frequency range. This is double our observation frequency. And sort of see these 2 thin, highly magnified lines. If you zoom in, you see that there are 2 pairs of caustics. So you have a pair of caustic here, a pair of caustic here. And notice that because your lens is chromatic, your caustics will sweep out a slope in frequency space, as Rob was talking about earlier. And notice that in general, they will merge at high frequency, because if you think about your phase at infinite frequency, you must only have the geometric contribution, because the geometric phase is proportional to frequency, and the DM phase is proportional to one order frequency. So at infinite frequency, you only have the geometric phase, which means you only have one image. So all the images at low frequency will in general merge at high frequency. So basically, the caustics are your boundary regions. So you have basically one image transitioning into three images and transitioning back into one image.
Is theory or observation?
This is simulation based on observation. Yeah. The phase screen inputted is observation, but this is the code is simulation.
So it's a simulation based with the same power law, right? That's
Yes, exactly.
And you put in a high energy cutoff.
Yes. Just zooming into one of the caustics, you see the interference pattern due to wave optics, and the maximum magnification we get is comparable to the maximum magnification we get in observations, which is about 70. But the time scale is very different. So in Rob's spectra, you see those double-peaked spectrum with separation of about 10 milliseconds, 5, 10 milliseconds. But here we have a separation of hundreds of milliseconds. So this is, so we can get the magnification right, but not the time scale. So this is a different simulation, just zooming in to the where the caustics merge. Essentially, this is a region where the three images all happen to merge together at the same time. And at that region, you have some very high magnification. So this is another simulation where I increase the frequency cutoff. So in this case, we get a lot more images which interfere with each other, and in general, they will not constructively interfere and get you a high maximum magnification. In this case, you only get 15, but the time scale that we get in here is comparable to a time scale in observations of about 10 millisecond correlation time. So either we can get the time scale right and not the magnification, or the magnification right and not the time scale. So the current questions that I have is, so we have a measure of the DM as a function of time, but ideally we want the measure of function of space because that's your actual lens. And the transition between these two is basically the velocity of the outflow. So I was wondering if you have enough information about to measure this velocity, and I'm not sure. The second question is, you have this one-dimensional measurement of the DM, but separately we have a measurement of the brightness, which in principle contains information about the other dimension. So from these two separate measurements, can we recover the 2D phase screen? And the third question, which is a big question, is ideally we like to simulate the actual system and see what we get for the DM. So apparently there's been some progress, but no paper yet.
What's that paper on Indius?
So I'll come back to it. Someone, yeah. Yeah.
Okay.
Yeah, and in summary, we have small structure in DM lensing, and this lensing is chromatic. And if we can forward fit the brightness, you can forward fit the simulated brightness to the observed brightness, then we can recover the lens parameters. And because you see lots of frequency structure, ideally we'd like to have a wideband observation, which we have proposed at GMRT, or Rob has proposed at GMRT, and we'll see get an observation in December.
Okay. Very important divide geometrical and dispersive
Yeah.
delay. Well, some observational test?
Sorry.
Some observational criteria.
Mm-hmm.
How to divide geometric and dispersive delays.
I see.
Well, because the main sense of this presentation is very important for this subject. Well, one short question, please. Please.
You looked at, in particular, using a steeper power law for your DM variations, because I would guess there are kind of two observational effects, spectral leakage from those very strong
Mm-hmm.
low frequency ones, and then high frequency noise, because you're kind of getting these lens effects in when you measure the DM in the first place, which probably enhance your high frequency fluctuations. Both would tend to flatten out that power law. So if you try to put 2.5 or something, which might be closer to a true value, how does that change this picture?
I have not tried that, but that's a good idea.
Well, just a quick follow-up question. What's the actual magnitude? I'm going to say the power spectrum. The magnitude of the electron column fluctuation at the wave number k is basically equals k minus 1/2.
2. Well,
No, just trying to say, what's the just take some characteristic times this wave number. What's the magnitude? How does the magnitude of the electron electron column fluctuation scale k minus 1/2?
Minus 1/2 is the standard deviation. So you multiply by 1 power of maybe
Exactly. So the lensing that goes as k to 1/2.
No, then you have to multiply by k squared because it's by double point. This is as dm. And the lensing is the second special derivative of dm. So it's completely dominated by the Fresnel cutoff. So in some sense, it doesn't actually matter a lot what you do because you're going to multiply by any power factor by 4 powers of k. So it's really k squared for the lensing depth. Meaning, it's all dominated by the Gaussian cutoff when you Fresnel integral.
Well, let's think. Well, the next.
Okay, now we're entering the episode 3. We're focusing on the magnetic field of this story. First is okay. Yeah. First, why are we interested in the magnetic field near the eclipse? That dates back to why there will be an eclipse. Like, at first, you think it's pretty natural that there's a binary thing, but since the size of the companion is less than half of the size of the rush lobe, and the size of the rush lobe is like less than half of the size of the large eclipse we see in around 300 megahertz. So which means that like near the eclipse region, like the electron density could be pretty low, like as you expected. That makes it hard to explain the mechanism in the eclipse. Like because electron density is low, it's like not likely to have strong free absorption, and also because the DM variation is not large enough, so the refractive eclipse is hard to explain. And also the radial flux density is not high enough in that situation, so the stimulated scattering is not as strong. So thanks to Chris' work, like we realized like 20 years ago that like it is really hard for a theory to explain the eclipse happening in this system. When you can't explain something, usually you will turn to magnetic field. So then Chris like proposed a mechanism of cyclotron-synchrotron absorption in this system. Like despite all this complicated like prediction of like how it gets into this situation, but we do want an electron density of 10 to the 4th, with it coupled with a magnetic field of 15 to 20 Gauss in that system to cause that eclipse. And that will cause a huge effect in the polarization observation of that system. So we are going to observe that to see whether this prediction is real or you actually need some, you actually overlook some mechanism that actually causing the eclipse. So the idea is that you need polarization study to understand the eclipse. But how are we going to do that? Usually you just measure the, because when passing the, in the presence of magnetic field, the linear polarization angle would rotate. Usually you just look at how much it rotates to see how much magnetic field you have. But the linear portion of a normal pulse in that 1957 is like this. So that makes it difficult to like directly measure it with a normal pulse. So how are we going to do that? Like before I enter the next stage, just in case, I want to clarify the notation I used. We are looking at the circular base of the polarization. So when you have an electromagnetic wave, and you can decompose that into a left circular polarization and a right circular polarization. And I use double L to denote the total flux of left polarization and RR for the right polarization. And if you sum them together, that is the total flux. And if you subtract them, that is the linear portion. And they're, circular polarization. Yeah, and their cross product is the linear polarization, which we can measure the Faraday rotation. Okay, like date back to 1990, like people have already tried to measure the difference between the arrival time of these two circular polarization. And this is their result. Although there are huge error bars, but it seems that it prefers to have a small magnetic field. But you can see that they're averaging 10 to 60 seconds, which is considered the velocity of the pulsar, which is a substantially large size. And maybe you are thinking like maybe they're averaging down the magnetic field because it's changing fast. So individual pulse observation of the magnetic field is important. And now we see that we are actually having a great chance to measure the magnetic field with single pulse, because this is the plot I steal from Rob's talk. We have lots of highly magnified events near the eclipse. So that will make individual pulse observable. And also we have those giant pulses that are highly polarized for us to see it individually. We get more than 200 pulses just by observing one eclipse with more than 20 signal to noise. So how are we going to use those individual pulses? For those lensed pulses, because they don't have much very high polarization fraction, the simplest thing we do is to look at the dynamic spectrum of them. This is the familiar slope. You have seen it twice in previous talk. And now we just do one step forward to look at the left circular polarization flux and the right circular polarization flux. And how are we going to look at this picture? The first quantitative thing we can say is that both polarizations are magnified simultaneously. And that is actually important because this is telling you that you are having a relatively smooth magnetic field. Why is this so? Because if you want to have a highly magnified image, you want all those flux in this large area to add coherently, which means that you want a flat wavefront. So the total phase from here to here should be, the change should be 0. And you can divide those change into the change from geometric delay, from the induced in the electron density, and also from the magnetic field. Like if you ignore the magnetic field term, it's very easy that you have a geometric delay like this, because close to line of sight, it arrives first, so its phase is the smallest. And you just like maybe, and when it's highly magnified, you just claim that the variance of the induced phase from Dm is like that. So these two cancels out, and you get a flat wavefront to give you a highly magnified events. But if you just impose a variance of magnetic field, which here I assume that it's less than 1 Gauss, then because the dm near the eclipse is pretty large, it can induce a large variance of phase across the image. And that is like 100 radian. And even if you can superpose that, the dm term could look like this as well, but because the two polarizations are opposite, the phase induced are opposite, you can cancel out one phase, you couldn't cancel out them simultaneously. So which means that even like 1 Gauss variance across the image that can completely destroy the magnified events in other polarization. So the only way for you to observe like magnify events in both polarization is to suppress the variance of magnetic field like that to be smaller than 2 pi. And that requires the variance of magnetic field to be smaller than 0.05 Gauss. So by simply looking at that they're magnified simultaneously, we can claim that it's a smooth parallel magnetic field with variance smaller than 0.1 Gauss. And that is like within one magnified image, which can span like several hundred kilometers. And the second thing we can look is that there's no significant displacement of these slopes, which can give us a quantitative estimate of how large is the mean magnetic field along line of sight. What do I mean by displacement of the slope? Because like the average magnetic field will cause the caustic to shift in frequency. If you are given like 10 Gauss magnetic field, then previously without magnetic field, the slope could look like this. Then for one polarization, it's shifted to higher frequency. For other, it's shifted to lower frequency. And it's very obvious that you'll see a distinct shift in the slope given like 10 Gauss magnetic field. And that is not the case we see. Like there might be like tiny difference in these two slopes, but generally they look pretty similar. They happen in a similar place and they're not shifted substantially. So that means that the average magnetic field should be roughly smaller than 5 Gauss. So just by one magnified event near the eclipse, given the high dm, we can quantitatively look at this and claim that the variance of magnetic fields is small and the mean magnetic field shouldn't be large. And also we have multiple other examples. I never see like magnification happen only in one polarization. But another interesting thing is that if you take one slice of here, which is 1 pulse, and you look at the frequency spectrum, you will see substantially difference in the flux variance in frequency space. Oh, sorry, I cut it. This is the frequency. This is the frequency. And the two colors denote the flux of two polarizations. And here is like you subtract the blue with the orange. And this is the circular polarization you get. So that means that you're actually observing birefringence in this system. And this is probably caused by the diffractive interference. If you have multiple images, you can see that there are always like dotted things. So the scintillation for the two polarizations is substantially different, but I haven't have a clear interpretation on that. But it might give you a lower limit of the magnetic field you have. And that is like from the lensed ordinary pulses. And another more like a traditional way is that you can look at the giant pulses because they have higher polarization fraction. You can select those that have higher linear polarization and measure the rotation in that. And from the Faraday rotation, you will get the magnetic field. which probably I'm running out of time, but so I'll do quickly. So I first did that for giant pulses out of eclipse. It converges at minus 50 rm. And it's clear, if you zoom into one, you'll see a clearly peak there. And I did that also for giant pulses near eclipse. But unfortunately, I didn't find very good examples in this case. But that is not very surprising because we only have one observation near the eclipse. It should be substantially improved if we have more observations. But I do seem to see a small spike that appears here, which if you zoom in, and this is the measured REM out of eclipse. And if you zoom in, each individual pulses that spikes has, you'll see a slight shift, but not that large, appears. But unfortunately, for those with higher DM, I haven't had very good examples. That's why I make it opaque. But for example, those, I definitely believe that it's real, that it has a RM of minus 98. Here I should correct the ionosphere contribution, but if the order of DM here is 10 to the minus fifth, then a shift of 50 RM would suggest a magnetic field of roughly 5 or 4 or something. Yeah, like order of that. Gauss. Yeah, 2, 3, 4, like that. So, but this situation could definitely greatly improve once we have more observations. So there are more things we can do because those giant pulses are very sharp, so it can give us better measurement of the arrival time difference between these two circular polarizations. So we can repeat the measurement 20 years ago to measure the arrival time difference between these two. But there will be some confusion of the morphology of that, how do you define the arrival point like that? And also, once we have better example of linearly polarized giant pulse near the eclipse, we can measure the depolarization fraction, and that can tell us the variance of magnetic field. So for each thing, the mean and variance of magnetic field, we definitely have multiple ways to measure that, and you can cross-check with each other. And so in summary is that polarization is important to understand the eclipse mechanism, and we could have lots of examples of individual pulses near the eclipse for us to measure the polarization. And by looking at the dynamic spectrum of length pulses, it can give us quantitative the order of magnitude parallel magnetic field and the variance of parallel magnetic field. By looking at the giant pulse, we can measure the RM, arrival time difference, and depolarization fraction. That can also give us these two things. And my current very immature, primordial result is that the parallel magnetic field is probably smaller than 5 Gauss, and the variance is smaller than 0.1 Gauss. That does not favor cyclotron-synchrotron model very much, but I don't want to claim that without the strict error bar. And also, the important thing is with wideband observation and longer observation, which we would have immediately after December, thanks to Rob, and we will have a good map of the magnetic field. And that is all. And thank you. It's very enjoyable to work in the group.
So I'm blown away by these results. It's fantastic to see some of these dynamic spectra in left, and right. And the comparison of the lensing model, so where you just have the lens, you have the opposite sign in the left and right.
Mm-hmm.
I would have expected that, and I think that's what you're seeing here. I expected that the differences that you do see in those dynamic spectra are really dominated by the rather than the curvature. The curvature is a second order effect compared to the gradient. So
you mean the magnetic, the RM, the gradient of RM itself?
Yes.
I think,
so
yeah.
When you showed those, you
Yeah.
showed that there are differences between some of these dynamic spectra, and that was obvious from the first one that you showed. And indeed, that's what the way I would interpret that is to say that the gradient in the phase is dominating over the second order moment.
Yeah, I think, yes, you notice that I put a delta.
I mean, that's the naive expectation from the theory.
Sorry, where did I? Yes.
If you just go back to that, if you go back one,
sorry. The gradient of this one is the gradient of magnetic field with absolute value of dm, phase of dm, or the gradient of phase dm with absolute value of magnetic field, which is
or some correlation.
yes, and sum together that is the gradient of the rm. Yeah.
Sure.
Yeah.
If you just go advance one slide, where you showed the dynamic spectrum.
Oh, yeah.
Those ones.
Yeah.
What's interesting to me is if I look at the top of that band there, because I can take my glasses off and convolve it with a larger point spread function, I see, the top third, a significant difference, or what I would
This one, yeah.
significant difference between these two, and I find that.
Yeah, there's a problem that always like confuses me is that like once you the refractive pattern should be more clear if you don't have the diffractive pattern. But once you have the diffractive pattern, like you look at a narrow width of things, then you get confused by that. That's why we need like wider band observation. Then it's more clear how the structure goes.
So a couple of slides further on, you show that there are left and right differences.
Oh yeah.
Well,
Yeah.
Anyway,
Yeah.
discuss that one.
well, I think short, very short question.
Yeah, sorry, it's a short one. Yeah. So the fact that you're saying that the magnetic field is slowly varying, do you think that suggests that it's probably the magnetic field of the companion star as opposed to the magnetic field that could be carried in the pulsar wind that's like in the eclipse region?
I think that should goes into Chris.
Okay, first off, remember the cyclosynchron absorption
Yeah.
very strongly dependent on temperature at moderate. We talked about if there's an equidistant magnetic field with the pulsar wind, harmonic of 7, maybe you're finding you need a harmonic of 20 or 30. But interacting with a relativistic wind, it's easy to get such high temperatures where it might work. That said, there are certainly other eclipse mechanisms that could be operating, like broadband pulsar emission can pump the Langmuir turbulence in ambient plasma and backscatter off it quite effectively at this close to the pulsar. But the other thing is that, as someone was mentioning, I mean, it's very plausible that in this situation the companion has magneticity. Very rapidly rotating. Hard to imagine it doesn't have a magneticity. So.
It could have magnetosphere, but what do you mean by very rapidly? Like
because
that?
the star rotates with the orbit, so it's a
No.
rapidly rotating star, so it must have a magnetic field, is the argument.
No. My thing is that like I might be slightly confused like whether these are there's a shift, but I'm pretty sure that like we observe that simultaneously means that the variance of magnetic field shouldn't be large. So if you want to say that it's varying like quickly,
No.
it has to be like
That's not what Chris is saying.
But
yeah,
again,
yeah.
what's the spatial scale over which you're probing these spectra?
Spatial scale.
100 kilometers or something, right?
100 kilometers.
Yeah.
Well, we will continue this very interesting discussion after coffee break, and now thank again.
I should give talks in the group meetings. Now I understand things. Both of them I understand much better from your talk than I've understood them from weeks and weeks and weeks and weeks. Yeah, very nice, really clear.